This work is on outlier-robust clustering of Gaussians and other non-spherical mixtures. This is a consequence of a merge of two papers, one by Ainesh, Bakshi, and Pravesh Kothari, and the other by Ilias, Diakonikolas, Samuel Hopkins, Daniel Kane, and myself. Ainesh and I will be giving the talk, and you'll see Ainesh in the second half of the talk. To set the stage, consider first the problem of clustering a mixture of k Gaussians. Here you're given samples x1 through xn, drawn from a mixture which is pairwise well separated and d-dimensional. And the goal is to output a 99% accurate clustering of these samples. We'll use Ci to refer to the individual components of this mixture. Before we go on, we define notions of pairwise well separation and alpha accurate clustering. We say that a mixture of Gaussians is pairwise well separated if every pair has total variation distance constant bounded away from 1. This constant could possibly be some function of k. Also, we say that an equipartition A1 through AK is an alpha accurate clustering of some other equipartition C1 through CK of a set of n samples if, possibly after some permutation, each AI covers at least an alpha fraction of some Ci. So in this case, you see that A1 covers at least an alpha fraction of C1, A2 of C2, and A3 of C3. With this, we move on to what we do in our paper. In our paper, we consider the problem of outlier-robust clustering of Gaussian mixtures. So before we define the problem, we actually need to define one more notion. We say that a set of n samples drawn from a distribution D is epsilon corrupted if an epsilon fraction of these samples are arbitrary and the remaining 1 minus epsilon n are drawn IID from the distribution D. So in the problem of outlier-robust clustering of Gaussian mixtures, you're given an epsilon corrupted set of samples y1 through yn drawn from your mixture M, and the goal is to output a 1 minus order epsilon accurate clustering of these samples. In a Simons research vignette by Diakonikolas, Mempela, and Woodruff, this problem is considered to be one of the most important open problems in algorithmic high-dimensional robust statistics. Here's some more motivation for why we consider this problem. Prior work on learning mixtures of k Gaussians either assumed some stronger notion of mean or covariance separation between its components, or was based on some algebraic structure of these Gaussians. So there is a d to the poly k time algorithm based on polynomial relationships of Gaussian moments for parameter estimation. Unfortunately, this is not robust to corruptions. Our work assumes that the components are separated in total variation distance. This is qualitatively the weakest possible notion of distance. Our work is also robust to corruptions. This puts our work in this line of other work on robust statistics. This started in the 1970s with Tukey and Huber, where the focus was on finding statistical estimators that are robust to corruptions. Recently, since 2016, there has been a lot of work focused on finding efficient outlier-robust algorithms. So there's been work on mean and covariance estimation, on regression, on clustering of spherical Gaussian mixtures, and now this. There is a lot of work here in this area, and there are a lot of papers to cite. Please look at our paper for a more complete list of citations. But here's another reason why outlier robustness is an interesting aspect to consider. Outlier robustness has motivated several new algorithmic ideas. For instance, a greater focus on order statistics, using filtering to remove these corrupted samples, where you filter using higher order directional movements, or coming up with algorithms that exploit more analytic instead of algebraic structure of the problem. In fact, our work falls into this final category, where we use a Sum-of-Squares program to solve the problem. And this is a more analytic instead of the previous algebraic approaches that were used to solve this problem. The main result of our paper is the following. Given an epsilon corrupted set of n samples drawn from a d-dimensional, well-separated mixture of k Gaussians, we recover a 1 minus k to the k times epsilon accurate clustering in d to the k to the k samples and n to the k time. Let's just focus on this statement for a bit. So I've written the statement for a mixture of k Gaussians. However, our result actually extends to a slightly more general set of distributions. One of the distributions that it does extend to is the uniform distribution over a sphere and affine transformations thereof. Also, not only do we find a 1 minus k to the k times epsilon accurate clustering, but we can also recover parameters of the components of this mixture to a small error and recover a mixture that is close to the original in total variation distance. One point to note is that this exponential dependence of k in the runtime and sample complexity is most likely necessary because of an SQ lower bound, which was shown by Diakonikolas, Kane, and Stewart back in 2017. Another consequence of our techniques is that we are able to do robust covariance estimation. So here you're given an epsilon corrupted sample from some distribution D with mean mu and covariance sigma. And we show that there is an algorithm that runs in n to the log 1 over epsilon time and outputs estimators mu hat and sigma hat, such that mu hat is close to sigma hat and mu hat is close to mu and sigma hat is close to sigma in Lerner as well as Mahalanobis distance. So this algorithm works for a wide class of distributions D, like Gaussians, the uniform distribution over the hypercube, or the uniform distribution over the sphere, and so on. Also, covariance estimation in Mahalanobis distance was not obtainable by prior work. With this, we move to one important technical aspect of our work. Observe that simply mean or covariance separation does not suffice to get separation in total variation distance. Here is a small example to show this. Imagine two Gaussians that are basically the same Gaussian on two low-dimensional subspaces, whose angular separation can be made as small as you want. Now, the mean and the covariance can be made as close to each other as you would like. However, these two Gaussians are always separated by 1 in total variation distance. This shows that simply mean or covariance separation is not enough. In fact, this is why previous results which assumed simply mean or covariance separation actually are assuming much stronger notions of separation than just separation in total variation distance. This leads us to an important lemma that we show relating TV's separation to parameter separation. So if you have two Gaussians that are close to 1 separated in total variation distance, then one of the following holds. Either there is a direction in which your means are extremely separated, or some direction along which your variance is extremely separated, or there are several directions along which your variance is separated by a little bit. So the final notion of relative Frobenius separation is the truly high dimensional notion. And this is what is new in our work. So previous results that tried to do this only relied on either mean or some sort of spectral separation, but that is not sufficient. If you are 1 separated in total variation, you are either mean separated, spectrally separated, or you're separated in this notion of relative Frobenius distance. So that's it for my part, and I'll let Ainesh take over and tell you guys about more technical aspects of this paper. Thank you.
All right, thanks, Sushrut. In the remaining part of this talk, I'll go over a bird's eye view of our algorithm, some new techniques that we introduce in this work, and how they compare to prior work on clustering mixtures of Gaussians. So let's start by making some simplifying assumptions for the sake of exposition. We will focus on clustering a mixture of two Gaussians, which we'll denote by script M. Such a mixture looks like this image here in two dimensions. Further, we will assume that we have access to n uncorrupted samples from this mixture M. A priori, this assumption might seem too strong and that it defeats the entire point of our result. But as we will see, our algorithm can be almost mechanically be made robust to this assumption. In other words, the transition from uncorrupted samples to corrupted samples is almost syntactic in our analysis. Before we discuss an algorithm, let us get comfortable with the following notation. We use script x to denote a set of n IID samples from a mixture of two Gaussians, with means mu1 and mu2, and covariance is sigma1 and sigma2. Such set x can then be partitioned into two sets C1 and C2, such that the points in C1 are drawn from the first mixture and the points in C2 are drawn from the second mixture. Since we are dealing with an equiweighted mixture here, we will roughly have half the points from each Gaussian. So now consider the following natural algorithm. For each subset S of n over 2 points from X, check if the points in S appear to be drawn from a single Gaussian. If yes, output this set as our estimate of the cluster and output the remaining points as our estimate of the second cluster. So pictorially, the strategy looks as follows. We start with a set of n points drawn from a mixture of two Gaussians. We then consider an arbitrary subset of n over 2 points from this set. One such subset can be represented by the golden points highlighted here. We then check whether these points appear to be drawn from a single Gaussian. As we can see here, it is visually evident that this subset does not belong to a single Gaussian. So the question that we are interested in is how to formalize what it means to appear Gaussian. Okay, so one strikingly useful property of Gaussians is that its low-degree moments have nice structure. So while this equation here might seem like a mouthful, let's parse it slowly. So we begin by considering a one-dimensional projection of the Gaussian along some direction v, and then center it around the mean. Then, in expectation, the tth power of this quantity is equal to some function of t times the variance of this quantity raised to the t over 2th power. So note that this inner expression actually denotes the variance along this direction v. Finally, we note that this structure holds for all directions v and for all even t simultaneously. Motivated by this property, we can then consider the following test. So given a set S of n points, let U be the uniform distribution over this set. Then, for all directions v, we can check whether the uniform distribution on our set satisfies an upper bound on the moments, as in the case of the Gaussians before. So this inequality here is often referred to as hypercontractivity of linear polynomials, since we are looking at univariate projections and raising them to the tth power. This is a linear polynomial here. And we're also relating the tth power to the variance, which is the second power, and therefore the use of the word hypercontractivity. Okay, we can now modify the first attempt from a couple of slides ago as follows. For each subset of n over 2 points, we check whether the empirical distribution has hypercontractive linear polynomials. If yes, we output this cluster. Further, this algorithm can be implemented efficiently, and it already works to give a robust algorithm for learning the means when they are separated. And this was shown in prior work by Kothari and Steinhardt and Hopkins and Lee. But now, let's see what happens when the means are actually the same. Here we have a mixture of two Gaussians that are concentric, but their variances are significantly different. And therefore, these two Gaussians are well separated. However, we will show that there exist clusters that do not belong entirely to any single Gaussian, which we will refer to as mixed clusters, which fool the hypercontractivity of linear functions test. To see this, we will consider the following mixed cluster, C hat, where 1 minus W fraction of the points are drawn from the first Gaussian, and a W fraction of the points are drawn from the second Gaussian. It is then not too hard to show that this set actually satisfies the hypercontractivity of linear functions property. Ignoring the expression that appears here, let us consider what is happening pictorially. We are given a mixture of these two Gaussians, and we can cluster them since most of the points belonging to the second Gaussian lie in this region, and they are significantly different from the points that are drawn from the first one. But there exists a mixture of these two Gaussians, which looks like the following distribution. And if we draw samples from this distribution, they continue to satisfy hypercontractivity. Okay, but clearly this cluster does not visually appear to be drawn from any single Gaussian. So the question remains, how can we conclude this formally? The main observation here is that the distribution is too concentrated in an interval around the origin, which is denoted by this red box here. This, combined with the observation that no single Gaussian over-concentrates in any given interval, will help us rule out such clusters. Note that if this set of points were drawn from a single Gaussian, either the distribution would taper off quickly here, or the variance would fall quickly to zero in this interval. And therefore it cannot have so much mass. Okay, so let us formalize this property of being not too concentrated in any interval. We begin by considering the probability that x drawn from a Gaussian lies in any interval of size delta scaled proportional to its variance. We say that the distribution is anti-concentrated if this probability is less than delta for all delta length intervals. So in other words, the probability that the distribution is concentrated in any interval of small length is small. Pictorially, let's start with the indicator function for an interval. Then the anti-concentration property says that the probability that x lies in this interval, plotted along the green curve here, is actually less than delta, which is the purple curve here. Further, for Gaussians, this holds for all delta greater than 0, as demonstrated here. And indeed, Gaussians are anti-concentrated for all delta greater than 0. We now show that mixed clusters, like the ones we constructed previously, actually violate this property of anti-concentration, and therefore enforcing it is a valid test. For instance, consider a mixed cluster where 60% of the points are taken from the first Gaussian and 40% of the points are taken from the second Gaussian. Then recall the PDF looks like the following. We can actually plot the probability that a point sampled from this distribution lies in an interval of length delta, and observe that this actually intersects the purple curve, which is the upper bound here, of course scaled by the variance. This suffices to conclude that anti-concentration is a useful test as it rules out such mixed clusters. Finally, we require an additional property where we soup up hypercontractivity of linear functions to hypercontractivity of degree 2 polynomials. These functions continue to be well behaved for Gaussians, as they again relate the tth power here to the variance of the degree 2 polynomial here. For example, consider the polynomial x squared. We can plot both the left and right hand side of this equation in one dimension and see that this property is actually satisfied. Okay, given these two tests, we can now describe an inefficient algorithm. We find a feasible solution to the following set of constraints. We want to find a subset S of size n over 2 such that S satisfies hypercontractivity of degree 2 polynomials and it satisfies anti-concentration. We know that this algorithm itself suffices to cluster the points. For the remaining part of the talk, we will briefly go over how to implement this algorithm efficiently. Here, our approach will be to appeal to the Sum-of-Squares relaxation of our problem. We start by enforcing constraints that select a subset of n over 2 points. This is relatively straightforward. We create n indicator vectors, n indicator variables, wi, where the first inequality forces them to be binary. The second equality forces n over 2 of these wi's to be 1. The third and the fourth equality here set the mean and covariance of the points indicated by the w's to be mu and sigma. The effect of this constraint can be summarized as follows. We want to pick a subset of n over 2 points from this input sample x such that the mean of the points is mu and the covariance is sigma. Next, we want to enforce hypercontractivity of degree 2 polynomials on this set. Hypercontractivity, to begin with, is already a polynomial inequality of degree 2t. Instead, we relax this and insist that it is instead the difference of these two quantities is actually a sum-of-squares polynomial. And this is a strengthening of the previous constraint, and we refer to it as certifiable hypercontractivity. Okay, the next constraint that we want to enforce on the samples is anti-concentration. But to begin with, this does not even look like a polynomial inequality. Instead, what we have here is an indicator of x lying in some interval, as denoted in this picture here. To relax this inequality, we consider the somewhat convoluted expression here and insist that this is a sum-of-squares polynomial. Intuitively, what we do is we approximate the indicator function with a squared polynomial such that it is epsilon close to the indicator function almost everywhere. This approximation, of course, incurs error near the spikes, and we have to account for it in the definition of certifiable anti-concentration, and therefore we have these additional terms here. The notion of certifiable anti-concentration has been extremely useful recently, and it was first introduced in the context of list decodable learning by Karmalkar, Kothari, and Ilias. and by Raghavendra and Yao. At a high level, it relates properties of low-degree moments to phenomena such as anti-concentration, and such a connection was not established before. Further, it can be imposed as a constraint in the Sum-of-Squares proof system, and we can optimize efficiently over it. More recently, it has found several other applications, including recent work on list decodable subspace recovery. Returning from our digression, we can now describe a sum-of-squares relaxation that we can then optimize over efficiently. We begin by a convex objective and consider the following constraints. The first set of constraints are our intersection constraints that indicate finding a subset of size n over 2. We then impose certifiable hypercontractivity of degree 2 polynomials over the set of points indicated by our intersection constraints. And then we also enforce certifiable anti-concentration over this set. Finally, we apply a simple rounding to recover the clusters. So in one slide, this is the high-level overview of our entire algorithm. Okay, our proof roughly involves two main components. We first show the feasibility of the polynomial constraints that we imposed in the previous slide. This involves showing that Gaussians are certifiably hypercontractive and certifiably anti-concentrated. Secondly, we show that we can efficiently optimize the polynomial system we described before. Here, we appeal to the proofs to algorithms paradigm that has been popular lately. And we also provide a new identifiability proof for mixture of Gaussians that is captured by the Sum-of-Squares proof system. While the last few words were not designed to make much sense, there are several recent talks that discuss these aspects of our work. For instance, Pravesh Kothari's talk at the PolyAlge seminar and Sam Hopkins' talk at Simon's Institute discuss these aspects of our work in more detail. Finally, I'll conclude with some open questions and future directions. Some concrete open questions include improving the dependence on K, the number of components, and the minimum mixing weight in our running time and error bounds. More broadly, can we robustly learn a mixture of all Gaussians? In this work, we focused on the special case where the mixtures are pairwise separated in TV distance, but can we hope to learn the parameters of mixtures that might overlap considerably? So this question was studied in a very recent and exciting work by Daniel Kane, who shows that you can actually do this for an equi-weighted mixture of two Gaussians. Finally, can we use the techniques that we developed in this work to obtain robust algorithms for other mixture models, inference problems, and supervised learning problems? Such problems were considered very recently in the context of Ising models and for supervised learning. I'll stop here and thank you for making it all the way to the end.